Guys, this is Chandrasekhar. We are going to talk about unsupervised learning. In this method, the data are grouped into clusters automatically. For example, in a cocktail party, different voices are overlapped. The task is to separate different voices. This is done by clustering the tone of sounds with respect to pitch. This is done without labels. Thus, learning with unlabeled data is unsupervised learning. Let's see k-means clustering. We are going to learn cluster samples that can put on line, on a XY graph and on a heat map. And lastly, we are going to talk about how to pick the best value for k. Imagine you had some data that you could plot on a line and you knew you need to put into 3 clusters. Maybe they are measurements from 3 types of tumors. In this case, the data makes 3 relatively obvious clusters. Let's see if we can get a computer to identify the same 3 clusters. It is done by k-means clustering. Take a unclustered data to cluster. Step 1. Select the number of clusters you want to identify in your data. This is k in k-means clustering. In this case, select k is equals to 3. That is, we need to find 3 clusters. Step 2. Randomly select 3 distinct data points. The blue, green and orange dots are the initial clusters. Step 3. Measure the distance between the first point and the 3 initial clusters. The blue marking is the distance from the first point to the blue cluster. Green marking is the distance from the first point to the green cluster, and the orange marking is the distance from the first point to the orange cluster. Step 4. Assign the first point to the nearest cluster. In this case, the nearest cluster is the blue cluster. Now we do the same thing for the next point. We measure the distance and assign the point to the nearest cluster. Now we figure out which cluster the third point belongs to. We measure the distance and assign the point to the nearest cluster, and the rest of these points closest to the orange cluster. So they all go into that one too. Now that all the points are in the clusters, we go on to Step 5. Calculate the mean of each cluster. Then we repeat what we just did, measure and cluster using the mean values. Since the clustering did not change at all during the last iteration, we are done. The k-means clustering is pretty terrible compared to what we did by eye. We can assess the quality of the clustering by adding up the variation within each cluster. Here is the total variation within the clusters. Since k-means clustering can't see the best clustering, its only option is to keep track of these clusters and their total variance and do the whole thing over again with different starting points. So here we are again, back at the beginning. The k-means clustering picks 3 initial clusters and then clusters all the remaining points. Calculate the mean of each cluster and recluster based on the new means. It repeats until the cluster no longer changes. Now that the data are clustered, we sum the variation within each cluster and then we do it all again. At this point, k-means clustering knows that the second clustering is the best clustering so far, but it doesn't know if it's the best overall. So it will do a few more clusters. It does as many as you tell it to do, and then they come back and return one if it is still the best. How do you figure out what value to use for k? With this data, it's obvious that we should set k is to 3, but other times it's not so clear. One way to decide is to just try different values for k. We will start with k is equals to 1. K is equals to 1 is the worst case scenario. We can quantify its badness with total variation. Try k is equals to 2. k is equals to 2 is better and now quantifies how much better by comparing the total variation within the two clusters to k is equals to 1. Now try k is equals to 3. K is equals to 3 is even better. We can quantify how much better by comparing the total variation within the three clusters to k is equals to 2. Now try k is equals to 4. The total variation within each cluster is less than when k is equals to 3. Each time we add a new cluster, the total variation within each cluster is smaller than before. And when there is only one point per cluster, the variation is equals to 0. However, if we plot the reduction in variance per value for k, there is a huge reduction in variation with k is equals to 3. But after that, the variation does not go down as quickly. This is called an elbow plot. And you can pick k by finding the elbow in the plot. How is the k-mean clustering different from hierarchical clustering? K-means clustering specifically tries to put the data into the number of clusters you tell it to. Hierarchical clustering just tells you pairwise what two things are most similar. Question: what if our data isn't plotted on a number line? Just like before, you pick 3 random points and we use Euclidean distance. In 2 dimensions, the Euclidean distance is the same thing as the Pythagorean theorem. Then, just like before, we assign the points to the nearest cluster. And just like before, we then calculate the center of each cluster and recluster. Although this looks good, the computer doesn't know that until it does the clustering a few more times. Question: what if my data is a heat map? Well, if we just have 2 samples, we can rename them as x and y, and we then plot the data in xy graph. Then we can cluster just like before. Note, we don't actually need to plot the data in order to cluster it. We just need to calculate the distance between the things. When we have 2 samples or 2 axes, the Euclidean distance is square root of x square plus y square. When we have 3 samples or 3 axes, the Euclidean distance is square root of x square plus y square plus z square. When we have 4 samples or 4 axes, the Euclidean distance is square root of x square plus y square plus z square plus a square. That's it, guys. I think you understood what is unsupervised learning and how k-means clustering works. Thank you.
Every day, a large portion of the population is at the mercy of a rising technology, yet few actually understand what it is. Artificial intelligence. You know, HAL 9000 and Marvin the Paranoid Android. Thanks to books and movies, each generation has formed its own fantasy of a world ruled, or at least served, by robots. We've been conditioned to expect flying cars that steer clear of traffic and robotic maids whipping up our weekday dinner. But if the age of AI is here, why don't our lives look more like the Jetsons? Well, for starters, that's a cartoon. And really, if you've ever browsed Netflix movie suggestions or told Alexa to order a pizza, you're probably interacting with artificial intelligence more than you realize. And that's kind of the point. AI is designed so you don't realize there's a computer calling the shots. But that also makes understanding what AI is and what it's not a little complicated. In basic terms, AI is a broad area of computer science that makes machines seem like they have human intelligence. So it's not only programming a computer to drive a car by obeying traffic signals, but it's when that program also learns to exhibit signs of human-like road rage. How will AI affect your job? Will it make your work obsolete? Just like the Industrial Revolution, it's not human versus machine, it's human and machine versus problem. The point is that artificial intelligence helps you accomplish more in less time. taking on the repetitive tasks of your job while you master the strategy and relationships. That way, humans can do what they do best: be human.